In this video, we will prove some properties of basis and dimension. First, we will show that every subspace of a finite dimensional vector space is another finite dimensional vector space. Moreover, the dimension of the subspace is less than or equal to the dimension of the vector space. Let us try to see a proof of this fact. First, we have to show that there exists a finite set that spans U. First, notice that as V is a finite dimensional vector space, there exists vectors v1, v2, etc. up to vn such that span of v1 to vn is equal to the vector space V. Now, if U is the singleton set 0, then U is clearly a finite dimensional vector space. On the other hand, if U is not the singleton set 0, then there exists some U1 which is not 0 that belong to U. Now there are two possibilities once more. Either U is the span of U1 or U is not equal to the span of U1. If U is the span of U1, then clearly U is a finite dimensional vector space. Now let us see what happens when U is not equal to span of U1. But before we go ahead, let us try to understand what we have done so far using an example. So we can take R4 as an example of the vector space, and the set of all x, y, z, w such that y is equal to z as the subspace. Now, if we take this particular example, it's very clear that U is not the singleton set 0. So we have to take some vector in the subspace. What is an example of a vector in the subspace? You can take, for instance, 0, 1, 1, 0. This belongs to the subspace U. Why? Because the second coordinate is equal to the third coordinate. And therefore, this vector belongs to the subspace. Let us call that vector U1. Now, let us once again check whether U is equal to span of U1. Notice that in this particular example, U is not equal to span of U1. So now we can discuss what we will do in the case where U is not equal to span of U1. If U is not equal to span of U1, then this implies that there exists some U2 in U such that U2 does not belong to span of U1. For instance, if we are taking our example from before, then notice that the vector 1, 0, 0, 0 does not belong to span of U1. So let U2 be equal to 1, 0, 0, 0. So this is an example. And now what will we do? We will look at span of U1, U2. And we will check whether U is equal to span of U1, U2 or not. Once again, in this example, we can see that U is not equal to span of U1, U2. So we will look at a vector that does not belong to span of U1, U2. Let's call this vector U3 and so on. In general, we can look at the jth step in this process. In the jth step, we see that if U is equal to span of U1 to Uj minus 1, then U is finite dimensional. On the other hand, if U is not equal to span of U1 to Uj minus 1, then we can find a vector Uj that belongs to U, but Uj does not belong to span of U1 to Uj minus 1. And this is the way we are constructing the vector uj. Uj does not belong to the span of u1 to uj minus 1. Because of this, you can notice that the vectors u1, u2, etc. up to uj are linearly independent from the linear dependence lemma. So the vectors u1 to uj are linearly independent. And here we are saying they are linearly independent in U actually. But as soon as they are linearly independent in U, they are also linearly independent in V. Because the condition for linear independence is the exact same in U and V. But notice that V1, V2, etc. up to Vn spans V. And we saw that the length of any spanning list is greater than or equal to the length of any linearly independent list. Therefore, these two should imply that J is always less than or equal to N. And therefore, this process that we described earlier should end before N steps. And in this way, we will be able to construct a spanning set for U. And that completes the proof. Once again, let us complete our understanding using the example that we were considering. Recall that in the example, V was R4 and U was the set of all x, y, z, w such that y is equal to z. And we saw already that U is not equal to span of 0, 1, 1, 0, 1, 0, 0, 0. Therefore, we should find a vector that belongs to U but does not belong to the span of these two vectors. Such a vector U3 would be equal to the vector 0, 0, 0, 1. Now notice that U is equal to the span of the three vectors 0, 1, 1, 0, 1, 0, 0, 0, and 0, 0, 0, 1. And that is how the process ends. At some stage, the span of the vectors that we have constructed would be equal to the subspace that we are looking at. And then the process will end. Hope you have understood the process well. Thus, we have successfully proved that the subspace of a finite dimensional vector space is another finite dimensional vector space. Now, it remains to prove that the dimension of the subspace is less than or equal to the dimension of the vector space. Notice that as U is a finite dimensional vector space, U will have a basis. Let U1, U2, etc. up to Um be a basis of U. Similarly, as V is a finite dimensional vector space, V has a basis. Let V1, V2, etc. up to Vn be a basis of V. Now notice that Ui belongs to U and U is a subset of V. Therefore, Ui belongs to V. Moreover, the list U1, U2, etc. up to Um is linearly independent as the list is a basis for U. Similarly, the list V1, V2, etc. up to Vn spans V as it is a basis for V. Now, we know that any list of linearly independent vectors should have less number of elements than any spanning list of vectors. Therefore, these two would together imply that M is less than or equal to N. But M is the dimension of U and n is the dimension of V. Therefore, we have proved that dimension of U is less than or equal to dimension of V. And that completes the proof. In this proof, we saw that every linearly independent list of vectors should have length less than or equal to the basis. Why? Because the basis is a spanning list of vectors. But the length of the basis is equal to the dimension of the vector space. Therefore, every linearly independent list of vectors should have length less than or equal to the dimension of the space. Moreover, it can be shown that whenever the length of a linearly independent list of vectors is equal to the dimension, then it indeed is a basis. Let us look at a proof of this theorem next. More precisely, we have the theorem that if V is a finite dimensional vector space, then every linearly independent list of vectors with length dimension V is a basis of V. Let us look at a proof of this fact. Let dimension of V be equal to n, and let V1, V2, etc. up to Vn be a linearly independent list of vectors. Now we have seen that we can extend any linearly independent list of vectors to a basis. Therefore, we can extend V1, V2, etc. up to Vn to a basis. But any basis of V has length n. Why? Because we saw that any two bases will have the same length, and this length is the dimension, and n was equal to the dimension of V. Therefore, any basis of V should have length n. Therefore, the only extension possible is V1 to Vn itself, because you cannot add any more vectors. If you add any other vector, then the length would be more than n. So you cannot add any more vectors. So these two conditions, they together imply that V1, V2, etc. up to Vn is a basis. This theorem is very useful or powerful because it reduces a lot of work. For instance, the list of two vectors 1, 1 and 1, -1 is clearly linearly independent. Why? Because 1, -1 is not a scalar multiple of 1, 1. And as these are two vectors in R2 that are linearly independent, they have to form a basis. Therefore, these two vectors will span R2. We don't need to explicitly show that they span. The theorem tells you that the two vectors will span R2. And that is the power of this theorem. Similarly, you can show that if V is a finite dimensional vector space, then every spanning list of vectors in V with length dimension V will be a basis of V. This proof is very similar to the proof of theorem 2 that we saw just now, and therefore I leave the proof of this theorem as a homework.